First order ordinary differential equations. So we will learn about how to solve the following types of first order differential equations. But first, what do we mean by first order? So differential equations only involving derivatives, first derivatives, dy over dx, y prime, so, or we denote it by y prime. And we will learn to solve 5 types of first order differential equations. First one is separable. Next week we will learn homogeneous differential equations and exact differential equations. And the following week we will learn linear and Bernoulli differential equations. But first we will study the existence and uniqueness theorem. So we want to solve a problem, but if the solution doesn't exist, then we just cannot solve it. So we make sure that the solution exists, and there is a way to show also the solution is unique. The existence and uniqueness theorem says that given a first order differential equation, let's say dy over dx is f of xy, so if the function f is continuous in some domain D containing x and y, and the second condition is the partial derivative del f over del y is continuous. So we want just the continuity in a domain D containing x and y, and let x0 and y0 be a point in this interval, in this domain. Then there exists a unique solution phi of this given differential equation dy over dx f of xy on some interval that satisfies the condition phi of x0 is equal to y0. So the continuity of f and its partial derivative is enough for the existence and uniqueness. So unique means there is only one solution. So unique, if you don't know the word, you may check it in the dictionary. Okay, let's give some examples. Okay, example. So given the initial value problem, so if you remember, we write IVP as short. So our initial value problem is given like this: dy over dx is equal to x squared plus y cubed. And when the initial value problem is given, there is also a condition given. Let's say we have y0 is equal to 1 condition. Oops. So this is our initial value problem. So there is one condition, y0 is equal to 1. So the question is, does it have a solution? Does the initial value problem have a solution? And is it unique? So this is our question. So what the existence and uniqueness theorem says that dy over dx is, so this is our f of xy. Our given f of xy is equal to x squared plus y cubed. So we only need to check the continuity. So this is continuous, right? There is no problem. It's continuous everywhere. So is continuous in every domain D. Also, we need to check the partial derivative del f over with respect to y. What is the derivative of f with respect to y? So f is x squared plus y cubed. We think x as a constant when we take the derivative. So the derivative of x squared with respect to y is 0. What about y cubed? So it is 3y squared, right? So this is also continuous everywhere. right? It is a polynomial. It is continuous everywhere. So we need to check this point x0 and y0. What is it in this case? It is given that y0 is equal to 1. So we have this pair x0, y0 is equal to 0 and 1 because we are given y0 is equal to 1. And so both are continuous. So both f and del f over del y are continuous. So any interval containing 0, 1, right? So are continuous on any or continuous in a domain. Oops, sorry. In a domain D containing x0, y0 is equal to 0, 1. Then by existence and unique theorem, solution exists and it is unique. Then by existence and uniqueness theorem, solution exists and it is unique. Great, so we know the solution exists. Now we will learn, not now, I will do one more example, but today we will learn some techniques to solve these differential equations. This type of differential equations, first order differential equations. We start with this separable type. Great, so let's continue to solve two more examples actually. So example, so the same question. So this time our initial value problem is, so we have dy over dx is given as y over square root of x. So let's say that we have this initial value problem. Or sometimes we can write the condition next to it. So y1 is equal to 2. So to use existence and uniqueness theorem, we need to check f and del f over del y are continuous or not. In some interval containing 1, 2. So we need to check this. So if we look at f y over square root of x is continuous everywhere except at x is equal to 0, right? It is not defined there, so, and it is not continuous there. What about del f over del y? What is the derivative of y with respect to, what is the derivative of f with respect to y? We think x as a constant, so this derivative is, it is equal to 1 over square root of x. So this is also continuous, so same thing here, or maybe everywhere except at x is equal to 0. But they are continuous in a small interval containing 1 and 2, right? If we stay away from 0, there is no problem. So we can find they are continuous in in a small, let's say, domain or interval. Sorry, I cannot write today. In a domain domain or in a domain or interval containing the points 1 and 2. So if we are stay away from 0, we are fine. So then by existence and uniqueness theorem, by existence and uniqueness theorem, the solution exists and it is unique. So now we have the same problem, initial value problem. Let's say dy over dx is equal to y square root of x, but the initial condition is this time y0 is equal to, okay, let's say y0 is equal to 3. So here you see we have a problem, right? Again, because of this point x0 and y0 is this time it is x is equal to 0. So this is x0 and this is y0. So we cannot escape from the point 0, where f and y, del f or del y are not continuous. So we cannot use the existence and uniqueness theorem. So the same problem, does there a solution exist? So is it unique? It's the same problem, but here since are not continuous and 0, so we cannot conclude. The existence and uniqueness theorem doesn't say the solution does not exist, so it doesn't give any information. So no information since f and del f over del y are not continuous at x is equal to 0 or x is 0 is equal to 0, we cannot use existence and uniqueness theorem. So there is no information from the existence and uniqueness theorem. So we don't know. The solution may exist or may not with this condition. So we force the solution to have the value 3 at 0. So we don't know. We don't know solution exists or not. So the existence and uniqueness theorem doesn't say anything about it doesn't exist. So it says only it exists if f is continuous and del f over del y is continuous around this point x0 and y0. Great, so I think this is all for existence and uniqueness theorem. So we can start now. Oops, why there is no the fun stuff. So finally we can start solving some differential equations, separable ordinary so really it is going to be fun. So great. So finally we will do something nice. Okay, I have to say that this is the easiest type of differential equation we can solve. So I will definitely ask it in the exam because I don't want anyone to get zero. So I hope everyone will solve this one and get at least 10 points or something. We will see. Okay, let's start with the definition. So definition. Okay, we say maybe we should say first order because now we are only concentrating on first order differential equations. So if an ordinary differential equation can be written as, so if first order, let's say first order ordinary differential equation so let's say we are given dy over dx is equal to f of xy. If we can be written in the form dy over dx is equal to f of xy. So we separate x's and y. Let's say this is a product of two functions, g of x times h of y. Then it is called a separable. So we separate the x terms and y terms, but we still have the multiplication also. It is called a separable differential equation. So how we will solve it? Okay, I will check out my notes. Okay, how to solve? Uh, it is very easy. How to solve? Okay, I will write it short. So we separate the system. So how to solve separable differential equations? So you are given dy over dx f of xy. Let's say g of x times h of y. So first thing you do is separate the system as. So what do we mean by separate? So we collect y terms to one side, x terms to the other side, right? G of x times d of x. So okay, like what we do is we divide by h of x and we multiply the other side with d of x. So we separate the system. We collect the terms which depends on y onto the one side and depends on the x onto the other side. We completely separate the x and y terms, and then what we are going to do is we just integrate, then integrate both sides. So we just integrate dy over h of y is equal to g of x over d of x. So that's it. We find the solution. Okay, let's solve some examples. So, okay, example. First one is, so we will solve a lot of examples today. So solve the or find the general solution, or let's say right, find the general solution of the following separable differential equation. So it is given as dy over dx is equal to, okay, let's start with easy ones, 3 e to the power 3x. So here there is no y term in the other side, but we can write this as, so we separate all the terms, y terms to one side and x terms the other side, and then we integrate 1 times dy. What is the integral of 1 times dy? It is y, right? What about 3 times e to the power 3x dx? So recall that the integral of e to the power ax dx is equal to e to the power ax over a plus c. So we don't forget plus c. So this is general formula, and in our case we have 3 times e to the power 3x, so 3 times e to the power 3x over 3 plus c, and we see that 3's are cancelled, so we have the general solution as this one. So this is our general solution. So you see, it is very easy, but you know, of course it is easy if you know how to integrate, right? So please recall integration from calculus, integration rules. Great. Okay, let's continue. I think it is 18. Okay, let's continue with another example. Okay, solve the initial value problem. Dy over dx is equal to 1 over x. Y1 is equal to 5. So the condition is given as y1 is equal to 5. Okay, let's solve this. It is separable. So it is a separable differential equation, but it is separable. We can separate y terms to one side and x term to other side. So this is dy is equal to 1 over x times dx. So when we integrate so recall what is the integral of 1 over x dx. So we know that it is ln absolute value of x plus c, right? Because we have to take the absolute value. Ln x function is it is not defined for negative values, so the inside of the ln x should be always positive. So we have dy y is equal to ln absolute value of x plus c. So this is our this is the general solution, but we are asked to find the solution which satisfy this condition y1 is equal to 5. What does this mean? If we put x is equal to 1, we should get y is equal to 5. So y 5 is equal to ln 1 plus c. So we know that ln 1 is equal to 0. So we have c is equal to 5. So what is the solution of the initial value problem? So initial value problem dy over dx is 1 over x with this condition. So we want this specific condition y1 is equal to 5 is, what is the solution? So it is y is equal to ln x plus c, but c is in this case 5. So this is our solution. It is as easy as this one. So you see, these problems are very easy to solve. Okay, let me do one more easy, and then we can start with we continue with the hard, difficult examples. So solve y prime is equal to y square. Okay, what about this one? So what about this one? Well, once we write y prime, so this means that dy over dx is equal to y squared. So if we separate the terms, y terms and x terms, we will get dy over y squared is equal to dx, and then we will integrate. What is the integral of 1 over y squared, or in general, so whenever you have recall. Okay, let's recall this. Okay, recall for x to the power n dx. So what is this integral? We know that it is x to the power n plus 1 over n plus 1 plus c. Of course, so this is the case when n is not equal to minus 1, right? So if n is equal to minus 1, this means that we have x to the power minus 1 dx. But we know this one is already, it is 1 over x, so we know it is ln x, right? So we had this case in here. So when n is not equal to minus 1, we have the integral is x to the power n plus 1 over n plus 1 plus c. But in this case, okay, let me write it here. And in this case, so this is 1 over x dx, and we know that in this case we have ln x plus c. And here we have something similar. Instead of x, we have y. So this was the recall. Maybe I will separate this. Okay, so we can write this y square as y minus 2 dy is equal to dx, right? So here n is equal to minus 2 in this case. So x or y, it doesn't matter. The same rule applies every time. So it is, the integral is minus 2 plus 1 plus, or we can write c the other side also, it doesn't matter. So this is equal to 1 times dx, the derivative is x plus c. So this is our general solution. What is it? It is minus 1 over y is equal to x plus c. So you can leave it like this. So this is our general solution. All right. Great. So I will continue solving problems in another video. Okay.